I'm going to go through how to solve an inclined plane problem, one of the classic problems in forces and physics. So here we have a 2 kilogram block resting on an inclined plane at an angle of 20 degrees. So I'm going to solve this problem without friction. So we'll assume that the plane is really slippery, frictionless, and we're looking for the acceleration down the plane. Uh, the main thing here is to draw the free body diagram for the block on the plane. This is similar to other free body diagram problems that we've done. And you begin by representing the mass by a dot. So here we have our 2 kilogram mass. And I need to figure out what all the forces are that are acting on that object. Well, if I were to draw them in my diagram, I might draw them on my block here as representing mg downward here. So I'll represent that vector as mg, the gravitational force pulling straight down. And we have a second vector, which is going to apply perpendicular to the surface, which we call the normal force. So that force is going to go this direction. Those are really the only two forces present in the problem. But we tend to like to talk about motion along the direction of the plane. So I would like to set up a temporary coordinate system that is what I'll call it is x prime, which is angled with respect to the original coordinate system, which would be x prime, y prime. And because the motion is going to be along the direction of x, I can talk about finding the acceleration down the plane. And so my free body diagram, if I were to represent that same dotted coordinate system on my free body diagram, I can see that my normal force N is oriented along this y prime direction, perpendicular to the surface. And my gravitational force now, you'll notice, is no longer directly downward. It is at an angle with respect to the coordinates that are oriented with respect to my plane, which means that I can break that y direction components of this force vector into x and y prime coordinates. And I'm going to erase my mg here and move it so that I can see my components. Let's get a different color. And so there's a component this direction, which would be the component of the force along the x direction. And then there's a force this way, which would be along the y prime direction. That triangle forms a right triangle. Now the question is, what is this angle? So if I put in an angle theta here, the question is, how does that relate to the angle of the plane? So I'm going to go ahead and do some geometry here. If I were to go back to my original plane, if this is an angle of 20 degrees, and I have my original force vector pointing straight down, you'll notice that that forms a 90-degree angle there, which means that if I make another angle that is now perpendicular to the plane, you'll see that this angle is 90 minus my 20-degree angle, so that would be 70. And so these two angles together must add up to 90, therefore this must be 20 degrees. In other words, the angle that is here that I've labeled theta is the same as the angle of the plane. And that will be true in all cases. So I can now represent these two components. The x prime component of the force, F sub x prime, is going to equal the hypotenuse of that triangle, mg, times the sine of theta. So this is going to be the force down the plane, and F sub y prime, or the force perpendicular to the plane, is going to equal mg cosine theta. So now I can apply Newton's second law to both of those directions. So Newton's second law for the sum of the forces in the y prime direction is going to equal, well, I have two forces. I have my normal force and my mg cosine theta pointed in the y direction, so I can represent them as n minus mg cosine theta equals 0. And some of my forces in the x prime direction are, well, I only have one. It's only pointed down the plane, so mg sine theta. And that's going to equal ma, because it's possible for the object to accelerate along the plane. It's not possible for the object to accelerate through the plane. That's why the y direction adds up to 0, and this one equals ma. And you'll notice from this second equation, I get that the acceleration is equal to g sine theta, the acceleration along the plane. And this is general for any inclined plane problem in the absence of friction. If we were to include friction in this problem, we would add in an additional force. So, pick another color here. How about green? We would see that in this original diagram, if the object is going to try to slide down the plane, then friction is going to point up the plane. That means I would add in a new force vector here in my free body diagram. And because that is in the x prime direction, it would now appear here in the x prime equation. So with friction, I would have some of the forces in the x prime direction would equal mg sine theta down the plane minus the frictional force equals ma. So you'll notice that the frictional force is tending to decrease the acceleration down the plane in a problem with friction, which makes sense. You have friction, you're not going to accelerate as much down the plane. And we recall that the frictional force, F, is equal to mu times the normal force. And you'll see that the normal force comes from the y direction. It's going to equal mg cosine theta. So this is a generic derivation of the force down an inclined plane. Let's go ahead and try and use this information for solving for specific numbers in the case of my 2 kilogram block on a 20-degree inclined plane. So here we've reproduced our problem, so we know that from our previous derivation that we have a force down the plane called mg sine theta, and we have no friction, so I can do sum of the forces in the x prime direction would be equal to mg sine theta equal to ma. You'll notice the acceleration down the plane is g sine theta, which would equal 9.8 meters per second squared times the sine of 20 degrees, and we can calculate that number. You'll notice that the mass doesn't matter. If I put a more massive object on here, it's going to have the same acceleration along the plane. This is very similar to the idea that if you drop any two objects in the absence of air resistance, they will fall at the same acceleration. The plane just gets in the way and takes a fraction of the downward acceleration. So the steeper the plane, the larger the fraction of gravity that's acting on the object. In the presence of friction, things will change because the mass of the object will contribute to the normal force, and so the object will have more force on it. But you'll notice if I derive that case for friction, remember we had some of the force in the x direction is going to equal mg sine theta minus mu times the normal force, some of the forces in the x prime direction, and the normal force came from equal to mg cosine theta. So we substitute that in here. So the normal force has gone up because the mass, if we increase the mass of this object, normal force goes up. But look what happens when we substitute that in. We say mg sine theta minus mu mg cosine theta equals ma. And the mass is still common to every single term. And so even though we increase the mass of the overall object, the inertia of the object goes up, and the net effect is similar.